So today we'll just go straight to dimensions. I understand that's where the issue is. As we know, dimension is just an operation that is used for basically determining the fundamental quantities which makes up a given derived quantity. Let's skip the talk and just go to the work. All right, so we have some important quantities that you must know their dimensions in advance, because you need them for the larger operations and the much more complex parameters you will meet in future. The first one is area. We all know that's length times breadth, so that means length multiplying length, so that's L square. We know after that is volume. Volume is length times breadth times height, so the fundamentals length, length and length are being used. Immediately after volume, density is the next. Density, as you know, is mass over volume. So if you don't know the formula, you will not be able to figure out the dimensions. Mass has the fundamental of m. We've already settled volume as L cubed, so this gives us mass and L raised to the power minus 3. Now in advance, what you need to know right now is the moment you know the dimension, you automatically know the base unit as well. What do I mean? The dimension of length is meters, and so since this area has L square, your unit will be meter square. This has L cubed, so the unit will be m cubed. Density comes out like this, so that means that the unit is going to be, the unit of mass is kilograms, the unit of length is meters, so raised to the power minus 3. After that, we now go to another set of quantities again, the simple one, starting with velocity again. Velocity is the displacement over time. Displacement is another measurement of length dividing a new fundamental quantity which we call time. So the dimension becomes L(t) raised to the power minus 1. Through the unit, you can now, through the dimension, you can figure out the unit. Length is in meters, time is in seconds, so that becomes meters per second. Acceleration is velocity over time. So what does that give us? We have already solved velocity as L(t) minus 1. So if we use this to divide time, the law of indices say when the base is the same, we subtract their power. So this will become L, the original t minus 1. This has invisible power of 1, so I'll subtract another 1. Because division, we subtract powers. So that finalizes our answer. Acceleration now becomes L(t) minus 1 gives us minus 2. So the unit will be, length is in meters, time is in seconds, and the power is minus 2 meters per second. Now when you've known velocity and acceleration, we can also use them to get some further quantities which utilizes a mixture of mass and these guys. One of such quantity which utilizes a mixture of velocity, acceleration and the rest is momentum. Momentum uses mass to multiply velocity, which means your m is multiplying the L(t) raised to the power minus 1. So that gives us m L(t) raised to the power minus 1. The unit is going to be kilograms meters per second. Then we go to force. Force uses mass times acceleration, as we already know. Your mass is m, and you already know your acceleration to be L(t) raised to the power minus 2. So what does that give us? That gives us m L(t) raised to the power minus 2. The next set of parameters that have the same dimension, we have worked on The dimension is the same as when you're solving the dimension for moment, couple, torque. So in all of them, we always do force times distance. For them, we already have our force. Even if you don't have, you just have to write the dimension for force because you already know it. Force is mass times acceleration, which is LT minus 2, now multiplying distance, which is L. So at the end of the day, we have m L square T minus 2. Now our next is, I don't even know where we stopped. Our next is power. Power is when you've solved your work done, you divide it by time. So it means that power is force times distance, which is how we get work done, then divided by time. From this area, you can just isolate their dimensions. We already know force is mass times acceleration, which is LT minus 2. Now multiplying distance, which is L, and all over time, which is T. Utilizing the laws of indices, we already know when the base is the same, for those multiplying, we add their power. So invisible 1 and 1 added together gives us L square. And then T, we add minus 2, dividing another T raised to power 1. So law of indices will subtract. So it's becoming minus 2 minus the invisible power of 1. This becomes mL square T minus 3. And the unit is going to be, mass is in kilograms, length is in meter, time is in seconds. There are some new concepts that you're not very familiar with. I'm going to solve all three by the side so that you will understand them when next you see a question with them. These three parameters, pressure, surface tension coefficient, and force density, they have similar looking formula. For example, pressure is force over area. Surface tension coefficient is force per unit length. Force density is the same force but divided by volume. So you see, please take note of these three guys. So for this one, we already know force is mass times acceleration, which is LT minus 2, dividing area, which is L square. Force over length, it means mass times LT minus 2, dividing length. While force over volume means mass LT minus 2, dividing volume, which is L raised to power 3. So using the law of indices here, 1 minus 2 according to the law of indices will be minus 1. So this one comes out as mass L minus 1 T minus 2. This one, the length cancels out, leaving me with just mass and T raised to power minus 2. And for this, 1 minus 3 will give us minus 2. So this mass L raised to power minus 2 T raised to power minus 2. So this is these are three closely related formula, the denominator just changing from length to area and then to volume. So take note, the unit of this will be kilogram per meter per second square. This one will be kilogram per second square, surface tension coefficient. This one will be kilogram per meter square per second square. All right, another parameter here, viscosity gradient. What is viscosity gradient? For those who will learn fluid mechanics later on, the formula is force divided by area and velocity gradient. So we already know what force is, we know what area is. What some don't know is what the meaning of velocity gradient is. So this is like this: area. Velocity gradient simply means change in velocity divided by x, where x means distance, so it's a measurement of length. So if we want to switch over now to dimensions, we already know force is mass times acceleration, which is lt minus 2, and we already know area is L square. So this velocity gradient now becomes, this is change in velocity, so it will have the dimension of velocity, which is Lt minus 1, but we are dividing it by the measurement of distance, which is length. And we are here at this stage. Let's simplify stuff. This is mlt minus 2 divided by L squared times, here we can already see what's going on, so this becomes just t minus 1. So we can now use indices to finish up. That gives me mass, nothing cancels. Then here we are going to have, there is invisible power of 1. We are going to have 1 minus 2 minus, 1 minus 2, sorry. So 1 minus 2 is what? Minus 1. While for the time, we have minus 2 subtracted from minus 1. So minus 2 minus 1. So you see that minus minus is going to change into plus in this case. So this finally becomes mass L raised to the power minus 1, then minus 2 plus 1 becomes T raised to the power minus 1. So the unit is kilogram for mass per meter per second. That is it for viscosity gradient. Let's look at some quantities that share similar units. One of such is pressure, which we know is force over area. It is the same as stress, which is also force over area. Dimensionally, it is also the same with the value of Young's modulus, which is also force over area. So these three people, if I try to work it out, it's always going to be, they are always going to be force over area. So that means mass times acceleration all over this L square. So that gives us mass L minus 1 T minus 2. So these three share the same dimensions. Another group of quantities that have similar dimension are work done. You see, kinetic energy, anything energy, potential energy, couple, torque, what else? Moment. All of these 1, 2, 3, 4, 5, 6 quantities all share the same dimension because their formula always at the end of the day comes with this force times distance. Even though kinetic energy is half mass times velocity squared, the unit still works as force times distance. So what would that be? Mass times acceleration, which is Lt minus 2, multiplying distance. This gives us ml squared T minus 2. So that is it for individual working of these dimensions. Now let's look at the uses of dimensions. There are two very outstanding importance or uses of, actually there are three. The first one we've been doing, which is using dimensions to figure out the base units. The moment you have the fundamental quantity, you can already tell what the unit is: kilograms, meter square, per second square. So that's the first importance of dimensions. We use it to figure out the unit of a given quantity. But two other outstanding importance of dimension is in verifying the accuracy of an equation. So if you're given an equation, we can use dimensions to figure out if such an equation is correct. Let's solve a few examples. Here we are to verify a few equations. It will not be exhaustive, but just take note, it's going to all use the same principle. So let's see, we have a few equations like this. All of these quantities will be verified using similar approach. Now let me explain how easy it is. All you have to do when trying to verify that two equations are correct, you just figure out the total dimension of what's on the left and then the dimensions of what's on the right. If the fundamental quantities have the same order, and when I say order I mean power, then that equation is correct. But in a situation where you have a quantity on the right that is not on the left, then it's an error, it's a wrong equation, and that is how we go. So let's work this out. Let me start with the first one. V equals U plus AT. We know that V, which means final velocity, is just LT minus 1. U, which means initial velocity, dimensionally is also LT minus 1. A, which means acceleration, we have already confirmed that it is LT minus 2. And time, T, which means time, we already have confirmed that that's capital letter T. So if we want to now show the workings, inserting their dimensions where they belong, LT minus 1 becomes equal to LT minus 1 plus acceleration, which is LT minus 2 times time, which is T. So what does that give us? Watch out for this plus here. So LT minus 1 becomes LT minus 1 on the left plus, by the time you do minus 2 plus 1 according to indices, you will still get LT minus 1. So if you look at this, you can see that the order of L is 1 and it is 1 also on the right hand side. The order of T is minus 1, which is also the same as what is obtainable on the right hand side. So therefore, such an equation is correct dimensionally speaking. The second one, upthrust equals density times gravity times volume. So upthrust is a force actually. So U, which means upthrust, it is the same as force. So we are going to work it as mass times acceleration, which is m LT minus 2. This one means density, and we have worked it out before as mass over volume. So mass m, volume is L cubed, so that's mass over volume, mass times L raised to power minus 3. G is acceleration due to gravity, acceleration due to gravity. So the unit will be, the dimension will be the same as usual acceleration. So that's LT minus 2. Normal acceleration formula. And V is volume. So that's L cubed. Now what do? We are going to write what's on the left and then manipulate everything on the right and see whether the M, L, and T will have exactly the same power, right? So upthrust is MLT minus 2. So MLT minus 2 will now be equal to, what did we get from density? Density is ML minus 3 times gravity, LT minus 2 times volume, L raised to power 3. So let's look. On the left we have MLT minus 2. This becomes, now mass has nothing else there, so that's just mass. We're using this is minus 3, all the coefficients of L. Minus 3 plus 1 is minus 2. Minus 2 plus 3 is now plus 1. So L power of 1, no need to write it. Then T was just minus 2. You see once more, everything on the left equals everything on the right. So this equation once more has been proven correct, dimensionally speaking. Over to the third. S is equal to UT plus half AT squared. Of course, we know that S stands for distance. So that means L. U again stands for initial velocity. So it's the same dimension as velocity, lt minus 1. T stands for time, which is just the dimension capital T. A stands for acceleration, which we have figured as lt minus 2. Now that we know that, let's write everything on the left. On the left we just have L, and it will be equal to ut. Where is u? That means lt minus 1 multiplying time plus 1/2 is dimensionless, so it doesn't affect our calculation. It doesn't have lt or anything. Acceleration is lt minus 2 multiplying time square t square. So what do we see? L becomes minus 1 plus 1 indices, because this t has power of minus 1, this t has power of plus 1, so minus 1 plus 1 cancels out, giving you just L left. Here L has nothing, so we have L, but here minus 2 plus 2 again cancels out. So now you see that the power on the fundamental is also the same, ignoring the coefficients. So this is as easy as it can be. Whenever you are asked to just verify that an equation is correct, there is no confusion. Just work out the dimension on the left, then piece out all the dimension of those on the right and manipulate them together until you arrive at a simple, straightforward answer. Once you've gotten to this stage, you have proven it, and that's all. Which means that you may already know what to do here as well. We have v squared, so this velocity we piece this out and just manipulate again. Let's give that a shot. So without wasting our time, we already know v means final velocity, so that's lt minus 1. We already know u means initial velocity, is still the normal dimension for velocity, lt minus 1 also. We know that a is acceleration, and that's lt minus 2, and we know that s is distance, that's just normal L. So let's manipulate and see. The square of lt minus 1, lt minus 1 should be equal to the square of this one, lt minus 1, plus 2 into acceleration is lt minus 2 times distance, which is L. Let's see that. When this is squared, or I didn't square them, when this is squared now, this gives me L square t minus 2. This one comes out L square t minus 2 as well, plus L times another L is now giving us L square, and this was t minus 2. So you see that that's always the case. Everything always comes out the same if the equation was correct. If I was manipulating and this came out maybe minus 1, the moment the total order of t is not the same on the left, I would say equation is not correct. But usually they just want you to verify that an equation is correct. This is all you need to do. Apart from deriving, getting the unit of a quantity, dimension is also used for verifying an equation. Now the third and most important function of dimension is also we use it to find the relationship between some quantities. So we use it to also derive an equation, not just to verify an equation. Dimension is used to derive an equation, and that's where the real work is. Not that it's hard, but you're going to see us do it together. So let's get right on. Carefully reading the question on your screen, we were told that period of oscillation may depend on a few parameters which they mentioned: mass, length, and acceleration due to gravity. Good. Now every time they've given you the values, the quantities that it depends on, we don't know how that dependence look, so we use variation symbol first. Now when we are about to convert it into equality, we introduce a constant, and because this is now a real expression, we will have to put an unknown power on each of them, and G as Z. Let me go again. When you're converting the proportionality into equal to, you must introduce some arbitrary powers on the quantities. If they said already that the left hand side depends on these parameters on the right, it means that dimensionally speaking, what's on the left should equal the powers, like the manipulation of powers on the right should finally equal this. So your first step will be to introduce X, Y, Z as powers. Now we do exactly what we did previously. We now try to piece out what the dimension of T is. T was called period, and period is measured in seconds, like time. So it's going to stay as T. M in the question symbolizes mass, and that's a fundamental quantity, so it will stay as capital M. L, which is length of the pendulum, will be given the symbol capital L. And this is acceleration due to gravity, so this is acceleration due to gravity. So we are going to give it the normal dimension for acceleration, which is LT minus 2. So after you got this, the next thing was to do the usual, which is piecing out the dimension of every single one of them. Now we introduce these quantities, these dimensions into the original equation. So since T is T, we will now have T equals, K is dimensionless. It can as well just go right away. We continue. Okay, let's just keep him there. Anyway, so mass is still mass with the power of X. L has been changed to capital L with the power of Y. But carefully observe for G. G represents this. So since mine was raised to the power of Z, it means I am now going to raise this new expression to the power of Z. So I have LT minus 2 raised to the power of Z. So just like we always do, working out everything on the right hand side. Mass is there, length is here. Let's open this bracket. When invisible 1 multiplies Z, we have L raised to power Z, and the T minus 2 is about to be raised to power of, is to be multiplied by the Z, so we now have minus 2Z. Good. Now at this stage again, we finalize. All the ones carrying L will be simplified into 1. So the K is still here, mass is raised to the power of X, we have length with power of Y and another length with power of Z. So that means that our length in this says we should add the power, so I'll say Y plus Z, and T minus 2Z. All we have to do now to finish what we've done is to compare powers. We compare powers on both sides. Now if we want to be honest, on the left hand side there was no mass, so that means the power of mass here must be equal to 0. So 0 is equal to X. Your first one has been done, so X equal to 0 because there was no mass on the left. We move over to L. There was no length too on the left, so for length we are going to say 0 is equal to this combination they are giving me here, Y plus Z. Okay, we'll keep it as our equation number 2 because for now we cannot find two people at once. Then we move to the last. I've settled mass, I've settled length. Now let's talk about time. So there was time on the left and the power on time was 1, so 1 will be equal to what we are seeing here, minus 2Z. This is equation number 3. So you can see that here we had 2 unknown, but here we only have 1 unknown, so it's easier to start with this. If we divide both sides by minus 2, we already have Z. So z becomes 1 divided by minus 2, which is minus 1 over 2. Now that you have the value for z, you can now bring z into equation number 2. Equation 2 said that 0 is equal to y plus, removing the z now, because we have z now, we'll put the minus 1 over 2. So what does that give us? If I take the minus 1 over 2 over, it becomes plus 1 over 2. That's equal to y. So my y is equal to 1 over 2. Now, it's one thing to have all the hidden values. It's now time to reinsert these values into the original equation. We were given that t is equal to k m raised to power x, l raised to power y, g raised to power z. So this now becomes t equals k, m is raised to power 0, so it's gone. Or let me still write it for now, m raised to power 0, l raised to power, we now have y as 1 over 2. So this is 1 over 2. And g raised to power, we have z already as minus 1 over 2. This becomes minus 1 over 2. So that simply means that our t is equal to, with this one vanishing completely, we now have k power of 1 over 2. For those who didn't this as well, you know it means square root. So this is square root of L. And when the power is negative, we can take it to the denominator, so the power becomes positive. And also, this becomes g raised to power half, right? Which is also the same thing as saying k into square root of L divided by square root of g. So last but not the least, this then becomes what? Two people have square root. So this is like saying k into one single square root of L over g. So go through this video again and slowly to understand what we did. It's very simple. Number one, you show the proportionality sign. Number two, you convert it into an equation by putting unknown values of their powers. So like x, y, z, you could choose p, q, r, you could choose a, b, c as the new powers. When you've done that, you open up each of their dimensions the way we've always done it. When you've opened up, the left hand side will be simple, but the right hand side, you have to now insert those dimensions into the values. And since they were raised to powers, it means you expand each of them according to that power, like we've done, and then bring all common parameters together and solve for the unknown values.